Ja, så er vi kommet til vores tredje foredrag i rækken her af vores Colorful Forskning i Støjen, og det er Grunde Jomas fra DTU Byg, som vil fortælle om, hvilken farve har en flamme i vægtløs tilstand. Vi har valgt at holde foredraget på engelsk, og det skyldes, at der sidder over 5.000 tilskuere udefra, og det vil nok være med til at øge mængden af publikum, også på sigt, for vi lægger de her sekvenser op på vores hjemmeside senere. Det kan man blive orienteret om på vores DTU Biblioteks hjemmeside. Velkommen til Grunde Jomas, og vi glæder os til at høre om det.
Thank you. Yeah, so I decided about half an hour ago that I was going to do this in English, given that we have a smaller audience in here and a bigger audience out in cyberspace somewhere. The slides are in Danish, though. So, what color has a flame in microgravity? This is a talk that I'm going to present research that I'm involved in with the European Space Agency, NASA, and also scientists from around the world. And the project is called the Sapphire Project. Here, we have a logo. I guess you can't see it, but on the right-hand side of the slides. So, just to start with, what is microgravity and what happens? I'll show us a slide with Chris Hadfield, who's a famous Canadian astronaut who also has about 20 million views for his Space Oddity music on YouTube.
And had to use equipment that was here on board the space station.
So what he's doing,
the coolest washcloths ever here on the space station. I'm going to show you.
He's asking
Here's one of our
what happens, or he was asked what happens if you turn a washcloth full of water in microgravity. So he's on the International Space Station doing this. And as you can see, the microphone doesn't need support. So now if you put the sound on him, I can just...
And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water is all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
So this is just to show, that things behave differently in microgravity, and so also does flames. And if you think that water and flames behave differently in microgravity, that has a consequence for fire safety that we research on a space station or in spacecraft, because you cannot use conventional suppression techniques nor detection techniques for the fire, because normally we put a flame detector or a smoke detector up in the ceiling because all the hot smoke goes up, but we don't know that that is going to happen, or we know that it's not going to happen in microgravity. So combined with the fact that not only, 20, 30 years ago, or until maybe 5, 6 years ago, it was NASA, ESA, the Russian Space Agency that were doing missions. But now we also have a lot of private and commercial programs that also need to have the same safety aspects in place. And in this case, the safety has been separated from the actors because most of them base their safety on research done by NASA, ESA, and the space agencies. So that is why we still work with the space agencies on developing understanding what happens when or if you have a fire in space. So one of the strategies is obviously to, you want to avoid fire, so you don't have any flammable materials, but that never happens because there's always exemptions. The clothing, all the paper bags, all the things that they have to bring with them. And then those, even if they're considered non-flammable, they're based on a pass-fail test that is conducted on Earth. So have we had fires in space? Yes, there's been fires in space on Mir. One was in an oxygen generator, and one of the astronauts said, "When I saw the ship was full of smoke, my natural reaction was to want to open a window, and then I was truly afraid for the first time. You cannot escape the smoke." For those of you who've seen the movie Gravity, then they have a quite vivid description of this, trying to escape out of the vehicle or using the Soyuz, as they did in the film Gravity. So this is the same one they used in this case, but they had 2 escape vehicles, almost like Gravity, and one of them was blocked access, and they had room for 3 astronauts, and they had 6 people on board. Given that this was the Russian space vehicle, I think they made a political decision to send off the American scientists first and keep the Russians in place on board. It took 2 days to achieve a normal indoor climate inside it, even though it was a small canister this size that burned. And like they said also, when I started spraying foam on the hot canister, the foam did not stick and had little effect, so I switched to using water. This created steam and just further smoke spread. So you can see, like, just as in the first video, the water doesn't behave like they had in mind. So, but still, this type of oxygen generator is in place on the ISS. There was another fire on Mir, and it increased the CO level, the carbon monoxide, and a double dose would have been lethal. So there are cases. So I started out to ask what the color a flame has in microgravity, and this is an experiment from Mir. It's a candle, and it's put on the side, to show the effect of microgravity. And you can see, as opposed to having a contour that you you expected it to have probably from a normal case, you would have something like this. It's almost completely hemispherical. And that has to do with that we don't have the buoyancy, we don't have the convective flow that is typical in a normal candle. Here it's the radiation that drives all the forces, and radiation is equal in all directions. So we create a very stable blue flame that is hemispherical, and the blue comes from that it's a cleaner combustion than the soot that we normally have in normal gravity. So what type of research do we do? Well, there's research that can be done. If we want to stimulate microgravity, you have drop towers where you can drop something in free fall and will obtain microgravity for maybe 5 seconds in the tallest drop towers. You can shoot up sounding rockets, and you can also do a very popular thing which is called vomit comet, parabolic flights that fly it's a regular jet, flies in a pattern like this, where you go steep up about up to 47 degrees. When I participated, we did 40, and it's extremely, extremely steep when you're in the airplane. I sat in the cockpit for some of them. And then when you go on the top, you get for about 22 seconds, you get microgravity conditions. And then you go down and you get hypergravity, which is about 2 times, in this case, you get about 1.8 to 2G. And those are the places which also are quite interesting because you try to jump, but you cannot really jump. I looked like this when I was in there. You can see this is the lights are in the ceiling. I'm pushing off with my foot from the ceiling in the airplane. I apologize, I don't look as interesting as Kate Upton when she was doing her microgravity flights. But so what does it, here's a movie just showing when people do this for fun. There's a company called Novespace in Bordeaux that does these type of flights for people that want to participate. This was a science class that was invited to go. They put table tennis balls in there with the researchers. We tried to stay a little more organized when we did the research. So you have here regravitation in 3, 2, 1, and boom. When we do this, when we do this for research, we did 3 days consecutively with 31 parabolas, one after the other. And that's why it's called a vomit comet. We do get medication, so we try to stay away from motion sickness, but still about 10% do throw up. When we do research in microgravity, this is a friend of mine did this, where they have a gas burner, and you see, and then you go into microgravity, there's a flow from the side, there's an ethylene flame, and you can see it's a very nice, again, blue flame, fairly stable, and it's a burner about here. And then you can soon see when it goes out of microgravity, after about 22 seconds, how the flame changes dramatically and actually extinguishes because it couldn't sustain the burning in the current flow condition. So the flame is very different, and these are things we try to study. And in particular, we're now developing a space experiment, and some of it is based and continuing some experiments that has been done in the International Space Station. Most of you probably know that there's quite a lot of research done on the space stations. That's that's part of the astronauts' job, that they have to conduct experiments while they're up there. They're not just hanging around. So most of them are qualified scientists because they are the ones conducting it. So in this microgravity science glove box, there's another experiment that is done. Here we have a fabric type that's considered representative of a material that is used for bags and so on. And we have an airstream from where I'm standing and over to the other side. And you have an ignition of this thin material. And also what is quite, so you can see it's a very, very stable flame. Also, obviously, if you had this horizontal plane in normal gravity, you wouldn't have a two-sided flame, you would just have it on top. So it's, again, a very different expression of the flame. And what we're looking at is, both the ignitability, but also the flame spread rate to try to create models so that we can estimate how materials burn in space, because they do burn. Because one of the things that is different from, for example, a space station than a lot of other places is that there's always a flow, because they have a recirculation indoor climate system. So there will always be a flow inside that can lead, to assist the burning. The burning is always slightly better when it's wind-aided. So the problem, though, with this type of experiments we've done in parabolic flights or on the space station is that the samples are typically very small. The one you saw here was maybe it's 2 centimeters wide, 8 to 10 centimeters long, whereas the type we can do parabolic flights, we may have about 20 seconds of good microgravity, and sometimes also there's something called G-jitter, which means that you have an unstable gravity, which is not ideal for conducting research. So what one of the leaders at NASA, Dave Urban, suggested, why don't we use one of these supply vehicles? First we looked at the automatic transfer vehicle from ESA, but we're now next year going to have experiments on the orbital Cygnus vessel. And what this offers is it offers a much larger spatial environment. It also, while the experiments will happen while this one orbits after it has detached from the International Space Station. And this allows us to conduct longer experiments with bigger samples so that we can know that, for example, edge effects and other smaller error, sources of error can be moved out, and also so we can know whether the estimates that we do on Earth are conservative. Because if we're conservative on Earth, then that is fine. If you're not conservative on Earth, then that's obviously a concern in our estimate. So this is just Cygnus from Orbital Sciences, some pictures showing it approaching the ISS. It's attached, and then it will leave. And the whole process that we're involved in, we're not the, this is Orbital Sciences that uses the Antares rocket that will be sent up from Wallops in Maryland. Our experimental rig will be cargo on this ship, on this vessel. And after it dedocks, we will have a cargo space. They will put other cargo on board, put trash or other material back. And then we will run our experiments remotely operated. There's no operator. The Cygnus is a doesn't re-enter. It doesn't land. It re-enters, but it burns up under re-entry. The whole vessel. It's actually, as you can see on the picture here. And while we're doing this experiment, we also have to download all the data through telecommunication links as it orbits, because otherwise, since it's destructed, we cannot save the data later. So it will orbit, the experiments will be conducted while it orbits. So we created this, and this is part, I'm a part of our coordinator for the scientific team The engineering work is done by NASA. They have a great experience with this. So we have a large sample about 45 centimeters by a meter that we're going to burn inside this vehicle, inside a module with a flow straightener with avionics and with data acquisition for temperature and movies and so on. And everything has to be self-contained. We cannot use a computer that is on board, so everything is one self-contained module that is remotely operated. And this is what it looks like with the cameras on the side. We have the burn sample, and currently there are 3 experiments scheduled. We have done all the samples. Everything is more or less ready. And the first one's going to be with the Orbital Sciences 5, and then Orbital Science 6 and 7. Those are what we refer to as the Sapphire experiments 1, 2, and 3. And they'll be conducted next year and the year after, based on when people decide to send up the orbital vessels. But they have the first 2 have been fairly on time, and there's one is going to be sent up on May 1. So they're following schedule fairly well. So next year, DTU will be part of an experiment that's going to be orbiting space and burning a large sample. So in summary, well, the first question is, the flames are typically blue, but also what we study is that flammability in microgravity is a research area with numerous unanswered questions. DTU is part of a team that has developed this research and is also doing research on flammability in other microgravity facilities. And hopefully it'll be a landmark for fire safety in space, and that we can continue to build on models and further experiments after that. And it will also be used as safety protocols both for space agency flights, but also typically for commercial flights that there is an increasing number of. So any questions? And here's just the names of all my collaborators, or most of them, research scientists from around the world, from this team.
Thank you. Sorry. Thank you to Jonas. Is there any questions? I was thinking that as the tourist in space is an expanding area, it is most welcome to know more about the security in space, of course. So you are testing different materials in this future missions?
Yeah, so we have the first, I only showed the first, in the 3 experimental series, the second one will actually have 9 different smaller samples. And so we're testing relevant materials that are considered interesting for different scientific parameters. But obviously, as you say, when you have space tourism, you will probably have a wider range of requests from people, what they want to bring. There's also been talk about a space hotel on the moon, which has a partial gravity. But the main point for what we do is to figure out if the test standard that we are doing on Earth is representative, or if not, conservative. Because if we can make a cutoff and be conservative and also create models, then the material we can put in various material properties and know the results, hopefully, for those 2.
Exciting. If there should be anyone who should be interested in this field or part of the field, they are very welcome to contact us. And if you want to get in contact with Grunde Jomas, you can do it through me, Ulla Svensmark, DTU Library. Thank you very much.
Thank you.